Hello everyone, today we are dealing with Young's double slit experiment. Before that, in 1665, a scientist called Grimaldi directed sunlight to a dark room through two pinholes on a screen, and with an expectation that he will get or he could observe dark and bright fringes when the beam interfered on the screen, but he got only uniform illumination. What is the reason behind it? You just think about it. And in 1801, Thomas Young demonstrated an experiment to show interference pattern. He used a monochromatic source instead of sunlight, and he used two pinholes, and he just incident the non-monochromatic source to this pinhole, and on the screen he got interference pattern like dark and bright fringes. And here from the pinhole we will get spherical wavefronts, and the spherical waves from the two pinholes interfere and you will get interference pattern. Here clearly the source is a monochromatic source, and from the two pinholes you will get coherent sources. So when coherent sources interfere at a point, you will get intensity distribution, that is you will get interference pattern. And in here the fringes were not clear, so he replaced the pinholes with two slits, and this experiment is known as Young's double slit experiment. He is the first person to demonstrate interference pattern to show light has wave nature. In Young's double slit experiment, we have one source of light, and we have two slits to divide the source into two coherent sources, and we have a screen to collect or to show the interference pattern. We can just look at the demonstration of the experimental setup. You have a source here, and you have two slits here. Let us take it as S1 and S2. S1 and S2, the dimension of S1 and S2 is a few millimeter or less than a millimeter, is like that order. And S1 and S2 are equidistant from the source S. Here S is a monochromatic source, and you will have a screen here. And let capital D is the distance between sources and the screen. Here these are the secondary sources from the primary source AS. This is a monochromatic source. Monochromatic source has same wavelength or one wavelength, and these are equidistant from S1 and S2 are equidistant from sources. So when a light ray reaches these, when the waves or light waves reaches the screen, they differ a particular phase difference, and when they are meeting at the center of the screen, just like this, from the center S1, from S1 and S2, they have same path, and there is no path difference between S1O and S2O. Therefore you will get a maximum or bright fringe at the center O. Have you got that? That is, from S1 and S2 you have same distance to the center O. So there is no path difference between the rays emerging from S1 and S2 at O. So at the center point O, you will get maximum intensity, or you will have brightness, or you will have bright fringe at O. And on the other sides of O, in this side and in this side, you will get interference fringes according to their path difference. According to the path difference between the waves emanating from S1 and S2. So here we are checking the path difference at an arbitrary point P. Let's draw the picture. This is the midpoint M, and from M the midpoint, then the screen is taken as O, and let P be the arbitrary point where we have to find what is happening, whether it is constructive or destructive interference. And from O, let X be the distance to P, and let us take this angle as theta. From the midpoint, this angle is taken as theta, and this is S1. This is the wave from S to P, S2 to P. So we have to find the path difference between S1P and S2P. And for that I am drawing a normal from S1 to S2P. Let S1N be the normal, and from this figure we can say that S2N is the path difference. Since after the normal you will have same path, that is S1P is equal to NP. So the path difference between the two waves is S2N. To find S2N, let us check what is this angle. When this angle is theta, we will have this angle as theta. Just check it out. So from this triangle, you have or S2N is equal to S2P square minus, S2P minus S1P. S2N is S2P minus S1P. So let us take this triangle. Here we will get let us take this triangle to get S2P. This distance, let us take the distance between S1 and S2 is small d. So this distance or M2 S2 is d by 2. So this is d by 2. So let us take it as O dash, and from the triangle P or dash S2, you will get S2P square, and S2P square is equal to, this is the hypotenuse of this triangle, and we can write like this: S2 or dash square plus P or dash square. S2 or dash is S2 or dash is d square plus P or dash is, this is x and this is d by 2. So the total distance from P to O dash is x plus d by 2. X plus d by 2 square. Likewise, taking this triangle, Just take it as O double dash. And what is this distance? This distance is d by 2 from S1 to M. This d by 2. So this distance is d by 2. So total distance is x. So this distance from O double dash to P, it is x minus d by 2. And S1 O double dash is d, the distance between the screen and the sources. So that from the triangle P O double dash S1 P square is equal to d square minus d square plus x minus d by 2 square. So we got S2 p square and S1 p square. From this we can find S2n. So S2n or S2p square minus S1p square is equal to, just number this equation as 1 and 2. So S2p square is d square plus x plus d by 2 square, and this is d square plus x minus d by 2. So d square plus x plus d by 2 square minus d square plus x minus d by 2 square. You will get 2xd by 2. Here you have, what will you get? 2xd xd minus xd. So 2x is 2xd. So we can write S2p square minus S1p square is S2p plus S1p into S2p minus S1p. So this is what we have to find, S2p minus S1p. So let us remain this portion here. S2p minus S1p square is equal to 2xd divided by S2p plus S1p. Here we are making an assumption that S2p and S1p is approximately equal to the capital D, the distance between D. There is a small difference between D and S2p and S1p. So we are taking S2p is approximately equal to S1p is approximately equal to D. So S2p plus S1p is can be taken as S2p plus S1p is approximately 2D. So S2p minus S1p is equal to 2xd divided by 2d. Just cancel this 2. So S2n, this is S2n, which is equal to xd by d, where x is the distance from x is the distance between O and P, and small is the distance between S1 and S2, and d is the distance between source and screen. So this is a path difference between S2p and S1p. And once S2n is equal to m lambda, where m is equal to 0, 1, 2, 3, etc., or an integer, you will get constructive interference. And once S2n is equal to 2m plus 1 lambda by 2, you will get destructive interference. So when the path xd by d is equal to m lambda, you will get constructive interference at the point P. When this condition is satisfying at the point P, you will get constructive interference, and once you satisfy xd by d is equal to 2m plus 1 lambda by 2, you will get a dark fringe at the point P. So according to these two conditions, you will get dark and bright fringes accordingly. So let us check what are the positions where we get destructive interference or darkness. We will have the condition for dark fringe or destructive interference xd by d is equal to 2m plus 1 lambda by 2. So x is the distance from the point O to the arbitrary point. So x, let us write like this xm, where xm is the any distance from O where destructive interference is occurring according to the value of m. So xm, where m is equal to 0, 1, 2, 3, etc. When m is equal to 0, you will get x0. So here you will have m is equal to 0 d into lambda d by 2 or d by lambda. Okay, so this is the distance d by lambda 2 is the distance where we will get the first dark fringe, where we are taking m is equal to 0. When m is equal to 1, x1 is the second dark fringe position. So you will get here m is equal to 1, so 3 by 2 lambda d or d 3 lambda by 2. Where in this distance you will get the second dark fringe. And let us check what are the places where you will get bright fringes. xd by d is equal to m lambda is the condition for bright fringe. So mth position, mth bright fringe position, you will get m lambda d by small d. For m is equal to 0, x0, you will have 0, x is equal to 0. X is equal to 0 means it is the point O. So at the point O, there is no path difference between the two waves. So you will get a maximum at the center. This x is 0 is equal to 0 means the center point O. You will get bright fringes, and let us take x1 is equal to lambda d by d, and x2 you will have 2 lambda d by d, and like that. And once you are taking the difference between the position, the x1 and x2, you will get like this. This is the first bright fringe, This is the central maximum. This is the first bright fringe and this is the second bright fringe. Like that. When you are taking the difference x2 minus x1, this is the fringe width or band width. The distance between two consecutive bright fringes, you will get lambda d by d. And once you are taking the distance between two consecutive dark fringes, you will get like this, d 3 lambda by 2 d minus d lambda by 2, you will get lambda d by d. So this is the fringe width. Let us take it as beta. So beta for bright and dark fringes is equal. From this equation, from this calculation, we can arrive in a conclusion that both bright and dark fringes have same fringe width. So we can say like this. The fringes produced by Young's double slit experiment are equidistant. Okay. So we will get alternate dark and bright fringes in Young's double slit experiment. These fringes are in parallel or they are equidistant. The thickness of the one bright fringe is equal to the thickness of one dark fringe, like that. The interference pattern produced by Young's double slit experiment is like this. These are the specialities of the fringes produced in Young's double slit experiment. So these are about the Young's double slit experiment. So let's stop this session for this time.